We're now going to take a look at some issues with regard to the security at the backend or on the server. Now, there are a very large scope of potential problems that come up when we start talking about backend security. This could include things like how you write your code, the language in which you write your code, the compilers that you use, the operating system, the developing environment, the development environment, and so on. In other words, you require a good understanding of multiple levels of the software stack to really say that your application is secure, right? So what we have over here is, just like in the case of the front end, non-exhaustive, but in this case, I would have to say it's a very non-exhaustive set of suggestions, right? It just sort of scratches the surface of the kind of things that you need to keep in mind. But what you need to understand at the end of the day is the fact that there could be problems where you least expect them. And so you need to be aware of possible things that can go wrong, and then understand this in a lot more depth and see, okay, what is the level at which you can sort of say, this is probably good enough for my application. Now, one of the first things that we need to keep in mind is something with related to package management, right? So now you have some degree of familiarity with developing Flask applications. And within those Flask applications, you would typically be using other libraries. It's quite possible that, for example, you have used the requests libraries. Depending on any new application that you use, you might, for example, try to use things like Google APIs, right? Maybe for authentication or for access to data storage or various other things provided by Google. It might be something for Markdown, basically rendering Markdown, okay? And the common way by which this is done is that we have something called a requirements.txt file, which specifies which libraries are being used by this particular Flask application. And as is generally considered a good practice, what you should do is create a virtual environment for your application and use a pip install or some kind of related command like that in order to install all the libraries that are required for your application. Now, while doing so, one thing that you need to keep in mind, and this snippet that I've shown over here is actually code from a Flask application, right? That it's a real Flask application that I've come across. You will notice that some of the libraries are just mentioned by name. So HTML5 lib, SendGrid, Babel, HTTP lib2, etc. just have a name associated with them. Whereas some other things like GraphQL core, Graphene, Google Cloud Tasks, and so on have a very specific version number associated with them. In general, it is better that you specify the version number. The reason being that from the time that you wrote the code to the time that you then try to install it, or maybe you are trying to maintain it and it might be 2 or 3 years later, you will find that HTTP lib2 or HTML5 lib has evolved. Some new features have been added, and as a result, there have been some breaking changes in what happened. Now, everything else, GraphQL core, Graphene, etc., are fixed, right? The exact versions that you wanted have been pinned into the system. They will install correctly and they should run without any problems on your system. But HTTP lib2 might actually end up having changed sufficiently that the way you use it might either be deprecated or might outright break. It might actually give you an error. Okay. So what happens when you are trying to do an upgrade? Let's say that you are trying to upgrade the version of Python that you use, right? And this, for example, happened not so long ago, maybe in the last couple of years, where Google App Engine at some point basically decided that they were no longer going to support Python 2 and everybody had to migrate to Python 3, right? So this was more or less a forced migration. They pretty much said, okay, as long as you want to use App Engine, we are simply not going to support Python 2 anymore. Was it a reasonable thing to do? That's a different question. Perhaps if you wanted to continue running with Python 2, you could have run your own services, right? Instead of using App Engine as a platform, you could have gone for direct infrastructure and used a bare metal or a virtual machine on which you install your own version of Python 2 and get things working, right? The point is, from Google's point of view, they were finding that maintaining and keeping security updates for Python 2 was becoming too much of a problem. So they pretty much said everyone who wants to use App Engine has to upgrade to Python 3. But then what happens? You automatically are forced to also upgrade the versions of Flask, which means that you need to upgrade the versions of all the libraries. And it is quite possible that you end up with some very delicate balanced situations where you end up with incompatible versions, right? And it also becomes quite problematic from the point of view of maintainability of the code. in some cases, if you are lucky, it might only sort of break some tests, right? Some tests fail. That's good news because it means that you had tests that caught those problems, and you can probably go and fix the code so that the tests now pass. But a more severe thing is if you did not have sufficient testing or sufficient variety of tests, you might also have introduced security bugs into the system. And this could be much more problematic if that happens. Now, this is a cartoon from XKCD, which is actually really prescient in some ways. The kind of problems that this is predicting have actually happened multiple times in the last few years. Right? Essentially, what it's showing is that you have large applications and a large amount of digital infrastructure which is being built up, and ultimately it's just being supported on, or all of it depends completely on one particular application, which could have just been maintained by a single person. And at some level, you don't even know whether that single person has just got fed up of doing this and decides to walk away, or at some point even decides that, look, they have had enough of people taking them for granted and actually decide to do some damage, right? The point is, by introducing some kind of problems at that dependency, you could affect multiple different applications. Now, this might sound sort of like a theoretical construct. It's not. Log4j is a logging library. It's a Java-based library used for logging information, right? Very simple. It's just logging information. All that it says is you can use the log4j library and essentially send it a message. It will save it in either as text into a file or into some kind of a database or something, right? Which has certain additional information such as the timestamp and standardized format, which allows it to be read in by other log analyzers and so on. Now, in around November of 2021, vulnerability was revealed in this. Essentially, it went something like this. If an attacker sends a specific type of HTTP request, and it could be fairly simple, right? I mean, all that they do is in the user agent header, they have some particular, they give it some malicious information, right? This is kind of an injection attack where you're giving in some malicious information, which normally should just have been written out as text into a file, and nobody cares about it after that. The problem is, vulnerable servers, ones that are running log4j, would actually try and interpret the information in this user agent, right? They would see that there is something LDAP server, and they would then try to actually go and query that server, which in turn could then send them some kind of a payload, which would be a Java executable perhaps, and that would get executed on the server. Okay, so this actually happened. In fact, it was a very big deal because there were a very large number of systems that were affected by the log4j vulnerability. The problem is this vulnerability had been around since 2013 or so, right? So it's not that it was just suddenly introduced by some random person. It was actually a bug in the code that had not been noticed, that had not been caught in testing, that nobody had really thought to look for until somebody came up with it in November 2021, 8 years after it had been introduced. So it's a very common library. It has excellent features, well supported, but it was, it just sort of got away under the hood. Similarly, another thing that happened is that there is a JavaScript library called faker.js. It's a module that's used for testing JavaScript code. And abruptly at one point, this was replaced with blank code, essentially breaking all modules using it. Why? Because the developer was unhappy with the way he felt that he was being treated. He felt too many people were taking his work for granted. He was unhappy about it. He felt he needed more recognition. He was also in a bad situation financially. But the bottom line is, just one person there was able to make a change in his code and push it to GitHub repositories, automatically breaking several other Node.js based modules or systems that were in existence all around the world. The bottom line is, this is what is called a supply chain problem, right? I mean, you are writing certain code, which in turn is making use of log4j or faker.js. Those are all part of your supply chain. And the more complex your supply chain, the bigger the likelihood that you might run into problems at some stage. how do you avoid such supply chain issues? One, the natural thought is, why not just reduce dependencies, right? Why should I depend on log4j or faker.js? The problem is you can't always afford to reinvent the wheel, right? Log4j was an excellent library. It had a good reputation. It is very well regarded, but it had a bug. Okay, well, all operating systems also have bugs, right? There are multiple scenarios where something like this could happen. So it's not unreasonable to say, log4j was a good thing to use, because otherwise you would have had to reinvent all the different conditions under which you need to take care of logging. There's a good chance that the code you write would have had bugs of its own, right? Now, another thing that could be done is version pinning, right? If faker.js, for example, if people had ensured that they were not using the most up-to-date and latest version of faker.js, they would never have got hit by the problem, because they would have been using only a version that did not get updated in this way, right? You also need to keep up to date with security issues. It's quite likely that people actually announce saying, okay, there is a problem, you need to go fix this, but it slips by you. You don't even realize that you are using it as a dependency, and therefore you do not go and update your code. The problem is none of this would have helped with something like the log4j vulnerability, because it was announced pretty much soon after it was discovered, but it had been in existence for much longer than that. Okay? But at the very least, these measures, reducing dependencies, pinning versions, keeping up to date with security issues, will reduce the chance of such supply chain issues affecting your application. Now, moving on to the server side, there are a few things that need to be done. One of them is with regard to server communications. Right? One is, of course, the fact that you just need to have very regular security. Right? Server maintenance is an art in itself, right? It's requires some amount of experience. It also requires following mostly well-known best practices, right? There are several techniques that are well understood and well known that help to reduce the chance of some kind of bugs in the configuration of a server, and that taking care of the security of that endpoint is something that is basically a system administrator's task. But as a developer, you also need to be aware of possible problems. From the pure communications point of view, it's very important to think in terms of end-to-end encrypted communications. That is to say, you might be thinking in terms of HTTPS, which is, after all, how a browser connects to any server. And now we have got used to the idea that whenever I connect to a server, I should be doing an HTTPS-based connection. Otherwise, it's potentially insecure. Insecure in multiple ways, right? One is that the fact that anybody who can see the packets on an HTTP link, right, which could be anybody who has access to one of the switches or routers between you and, let's say, the bank to which you are trying to connect. If you were using HTTP, they can read all the information that's there inside your packets, right, including your account number, your passwords, and all of that. HTTPS pretty much takes care of that for you. It ensures that there is an encrypted channel between your browser and the end server. So no matter who has access to routers or switches in between, they will only see sort of random looking data. They can't figure out what the content of the text is. Okay, so HTTPS effectively takes care of securing the wire for you. Now, the point is, you should also do this between servers, because nowadays, especially, we have scenarios where you have multiple distributed servers. One of them would be a front-end server, one might be a database server, one might be a Redis cache, another might be a Celery task server. The communication between each of these, as far as possible, should also be encrypted using transport layer security, or TLS, right? This is just to ensure that the chances of somebody either injecting new information or leaking information based on snooping on the communication between servers should not happen, right? And another step that you can take in this direction is to allow only authorized communications. That is, only requests from known clients will be accepted by the backend servers, right? In fact, you could go to the extent of saying that backend servers cannot be directly accessed even by clients, right? Or rather by browsers, right? Only certain front-end servers are allowed to make requests to the backend. And by ensuring that you do network level filtering and some kinds of authentication, perhaps using some certificates to authenticate and so on, you can ensure that this does a fairly thorough job of making the backend servers quite safe and at least reduce the chance that they are going to be attacked directly from outside. A related problem, more from the network point of view on servers, is something called denial of service. Denial of service is not really trying to leak information, right? It's not trying to extract information or personally identifiable information. Essentially, it takes a different approach. What it says is, look, there is some kind of a high traffic website where there's a lot of, the application developer, in other words, is having a good website with a lot of traffic on it. What happens if we disrupt it? Right? Even a few seconds of disruption on something like Amazon or Facebook or Wikipedia or WhatsApp is going to be quite problematic, because lots of messages are lost, lots of people are unable to purchase things, right? Lots of, in other words, legitimate commerce traffic is lost. Okay, and it can have a big impact even in a few seconds. So denial of service basically aims to say, okay, we'll just bring down the server and make it unavailable. So this is more like a brute attack, right? On the other hand, you could also have a scenario where by doing a denial of service, in order to bring or recover from the denial of service, the application developer is in such a hurry that they make mistakes and they bring up something which is not quite as secure as it should have been, right? Potentially giving an attacker window to try and extract information that they actually wanted. A variant of denial of service is what's called distributed denial of service. The kind of traffic we are talking about here is huge. In last year, Cloudflare, which is one of the main hosting companies for across the world, reported that they had seen and successfully blocked a denial of service attack which had a total bandwidth of something like more than 2 terabits per second. That is, across the globe, the number of requests that were being sent was several million requests per second, amounting to something like 2 terabits per second of data hitting servers. Okay. The only way to even protect against something like this is to have a planet-wide mechanism. That is, you have people like Cloudflare or Google or Amazon with resources everywhere on the planet in such a way that they are able to route around such issues. But even for them, this becomes quite difficult. Okay. So once again, like I said, this goes more into the realm of network and operating system level issues that need to be faced. It may not really be feasible for the app developer to do much about it, except to be aware of it and to know how to recover if something like this happens. Now, DevOps in general is a somewhat generic term, right? What exactly does it mean? Is it development operations, developer operations? The point is, it mainly refers to things that are involved in setting up and maintaining servers and also deployment of the code, right? And one of the most important things that you need to keep in mind when looking at this is, how do you automate as much as possible? Right? And we have already discussed this in the context of things like CI/CD, right? Continuous integration and continuous delivery. And the idea out there is to use either things like GitHub workflows or GitLab pipelines in order to automate processes. Every time that you have a commit to a particular branch in your Git repository, some sequence of commands is executed, right? And that should hopefully automatically compile your code, run a bunch of tests against it, push it onto a staging server, again run some tests on an actual deployment. And once all of that is done, perhaps actually push it out to production as well, right? Automation is important because it reduces the chance of mistakes happening just out of human error. And this is a very important, this is one of the key reasons why DevOps is important to start with. Now, all of those were with regard to the servers. There are a couple of issues. One of them is with regard to password guidelines that I wanted to also bring up, right? And this is actually quite an interesting document. It is from the NIST, which is the National Institute of Standards and Technology in the United States, right? Which talks about the guidelines for using passwords. So this NIST document gives a lot of information about what should and should not be considered when you are taking into account implementation of passwords. Okay, unfortunately, it's a fairly long and complex formal document, which means that actually understanding what it says requires fairly careful reading. Okay, so there are certain sites that have done a better job of sort of interpreting what this is and converting it into English that is easier to understand, right? An example over here is this website that I'm mentioning over here. I'm not sort of recommending it specifically as the guidelines themselves. It's probably better to read through the guidelines, but this does a good job of sort of explaining the core ideas behind it to you, right? And there are some very interesting things which, unfortunately, when you look at it, you find that are actually being violated by many of the websites that we see today, right? Now, one of the things to keep in mind, for example, is the conventional wisdom, which says that a complex password is more secure, right? And what the NIST guideline says, that's basically not true, right? So when somebody goes and says, use a password that has uppercase, lowercase, special character, numerical digit, at least 8 characters long, fine. 8 characters long is good. Everything else about it is probably unnecessary, right? And essentially, the point is by having a long password, which is hard to guess, which could be as simple as taking some 2 or 3 words and putting them together, right? You are making it extremely hard for a brute force system to be able to break the password. Whereas it doesn't matter whether you use uppercase, lowercase, special characters, and so on, right? All that does is it makes it very hard for a human being to remember the password, right? And it actually reduces the length, or in fact even increases the chance that they will actually just write it down, right? Even things like periodic resets, you have to change your password every 3 months, right, is ridiculous, because what ends up happening is people forget passwords, so they are forced to write them down. Okay, and several things, right? I mean, there are things that say use only a virtual keyboard. You are not allowed to copy and paste your password. This makes it problematic, for example, to use things like automatic password managers that allow you to store the password in a extension and just paste it in as required, right? So there are many such guidelines that have been given in the NIST regulations. The bottom line is unnecessary complexity does not help, and making it hard for the user to remember and type in a password will only encourage poor habits. Okay? So these are good things to keep in mind, because at the end of the day, when you are trying to implement authentication in an application, you should probably be aware of these principles. One other thing, of course, is especially if you are storing your own user passwords. That is to say, you're creating user accounts on your system rather than, let's say, using something like Google authentication, right? Ensure that you store only encrypted passwords, right? This is a standard technique that has been around for decades, right? Where it says that you do not actually need to store the password itself anywhere on your system. What you need to store is only an encrypted or a one-way hash, right? So a hash is essentially something like a one-way function, a function that where you cannot easily find the inverse of the function, right? So if I give you the password, you can find out what the hash is. But if I give you the hash, it's nearly impossible. It is more or less impossible to get the password back. Okay. So what that means is you take only the hash and store it on your server. And if you want to check a user's password, that's easy. You take the password, you encrypt it, and you check whether the hashes match. But you never store that password after that, right? You discard it as soon as you are finished checking. Things like this sort of reduce your attack target. Even in the case that you do have a problem and your application gets hacked, you are not leaking information, you are not leaking passwords to the attacker. A final word related to DevOps, right, is with regard to how you deploy an app, right? Once again, automate access as far as possible, right? With regard to the actual deployment and accessing the systems on which you have deployed, use SSH, use encrypted communications always, right? Do not use any kind of non-encrypted access to any of your systems where you're either testing or deploying your application. Now, most applications also have certain kinds of secret tokens, right? So if you're using JWT tokens, there is some kind of a secret that's used in order to generate the token. Similarly, there will be some kind of salt used for the password hashing. There will be some other credentials that are required for passwordless access to certain APIs, right? All of those should be stored. There are standardized techniques that are available for storing such things, and those should be made use of, right? And in particular, passwords and so on should never go into a Git repository, because once it goes into a Git repository and it's in version control, it can effectively never be deleted from there. Okay, so this is something that you need to keep in mind. And of course, everything, including the access to your databases, should be kept secure. One last thing, in some sense related to the log4j topic that I had mentioned to start with, but from a different point of view. Log4j over there was actually showing that there was a problem with logging. But in general, logging is actually essential, right? Whenever there's a problem, it allows you to backtrace and see what were the most recent requests. Were there any signs in the logs that their problem was about to come, right? Problem is that too much logging can affect the performance. You might end up spending more time writing data out to a log than actually returning useful data. Or you might also start to incur large costs from the point of view that you actually have to store all the log information. So ultimately, it becomes a balance between the performance requirements of your system and how well you can debug, right? One thing you should always ensure is that regular summaries from the logs should be stored in your system, and some kind of time series analysis is used for identifying problems. And of course, you can control the size of logs by doing regular log rotation to avoid unnecessary growth. So to summarize all of this, application security is a vast topic, right? It requires a breadth of knowledge from application developers, including going all the way up to system administration, right? You cannot afford to be ignorant of system administration if you want to scale or have apps that scale up beyond a point. As an app developer, you need to understand the privacy implications of your application. Collect only the data that you need, because ultimately you will be held responsible if there is a leak. And finally, what you need to do is to be able to implement whatever security is needed in order to achieve the levels of privacy that are required by your system.